I'm Mateusz. I work as a data engineer here at Base, and my talk is about Python for data science. So, few questions at the beginning. Who knows Python? Just the basic syntax. It will be use it in. Okay, cool. And who uses Python for their everyday job? Anyone? Few people. Okay, and another question: who works with data in general? So, I mean, either building machine learning models in R or with big data, stuff like that, generally. Okay. Cool. So the goal of this presentation is to show you how Python's human-friendly syntax, awesome data libraries, and whole environment and big data integration provides everything you need for working with data. So as you know, Python is dynamic general purpose language. You can use Python for scripting, for building web applications, scientific computing, and stuff like that. And and also by using all of those Python stuff, you can build powerful data-driven applications. And what do you need for that? I'll cover things like research and development environment, data analysis and visualizations, machine learning, offline big data or so-called batch processing, and real-time big data, stream processing. So, things like Hadoop and Storm in Python. So the content is quite broad, and I won't cover every detail, but I wanted to give you an overview of this Python ecosystem. Okay, so let's get started. First thing, environment. Working with data is quite different from regular programming because code and data are strictly linked. What I mean is often you process data in some way using by writing some piece of code, and when you see the results, you decide what is the next step, right? So you cannot really plan in advance and build entire data product at once. You need to look into the data and, based on that, format your next steps. You also need to share your research because, working with your other data scientists is very important. So you want your environment to, easily share your code and your ideas and your results. And as I mentioned, shortening that feedback loop between data and code is really important. So that's what you already see and what I'm using for today's presentation. It's called iPython Notebook, and it covers all of these requirements. So this is an interactive web-based Python shell. You can mix code, output, and nodes within it. And it provides a really nice environment for working with data. So here's some examples. This is a cell within iPython Notebook, and I can run regular Python in it. I can execute this cell, and it immediately shows me the result of this, executing this line, right? So this is the basic list from 0 to 9, and I can execute another cell that maps, assigns those calls to some variables, right? I can, of course, change this. So, for example, let me execute this cell again. So this prints the output of the previous cell. And I can change it to, for example, let's change the range to 5, and actually not squared, but cubed. Okay, so I executed this cell, and it executed this cell within the actual context of this application. So if we'll try to print this thing, it should print a new L because I assign a new object to this variable. Squared should be not touched because I assigned another, to another variable the new cubed list. So as you can see, I can execute my code, cell by cell, or even change the cell and rerun the same code again. It also supports some nice helper methods. So for example, you can see the source code of your objects, or it also has support for some tips and hints. Okay, so this is the iPython notebook, and I will cover many more features about this thing in the further steps. So let's move to the data analysis part. So what's data analysis? Basically, you want to load your data, parse it in whatever format it's stored. You want to manipulate your data, so slice some subset of the data, sort it by some criteria, compute statistics, transform, and try to find some patterns in data, right? Or prepare it for machine learning applications. Important part of it is also visualizing, so generally plotting and stuff like that. And after you are finished with your data analysis, you can either export it or prepare it for machine learning applications, right? So pandas is great for working with tabular data. This is the Python library that enables you to work with tabular data. And for plotting, I mostly use ggplot. Any R enthusiasts here? Yeah, so Python has port of ggplot, and ggplot is really great. So let's get started. I have a small data set. It's called adult data set. I downloaded it from the UC machine learning repository. So it describes, people, adults, with the context of income. And we have a classification task here based on all those variables and attributes like age of the individual, type of employer type, highest level of education, marital status, and stuff like that. Based on all those variables, we need to predict whether the given person, their income would exceed 50K or not. Okay? So yeah, let's analyze this data set. So first thing is reading the data set, and what is the most popular format of the data? It's CSV, of course. So let's load the CSV file. So pandas has support for many different formats, including CSV. So I just executed this cell, and let's take a look at this data set. So the head method would print me the header with the column names. So that's how this looks. Yeah, and based on that, I can start analyze the data. So basic thing, check the number of examples and variables, and slicing. So I can select the subset of rows from 2 to 4, actually to 3, subset of columns, or combine those two to select subset of cells, right? Okay, so let's start analyzing this data set. First variable is age. The most basic thing we can do is to compute some summary statistics. So if I execute the describe method on the age variable, it prints the overall count, mean, median, standard deviation, and basic statistics that describe this variable. Of course, those summary statistics can sometimes be misleading. So it's often good to plot your data as a histogram, for example. So here I use ggplot. ggplot is very simple tool for basic plots. So I provide my data set. I define my aesthetics. So on x-axis, I want to see the age variable, and I decide what type of plot I want to use. So there is a histogram, and if I execute this, I see in the browser the output of plotting this variable, right? So now we can think what kind of distribution this is. Any ideas? Exponential? Not really. Maybe it's a log normal. We can try that. So let's plot the density function. So it's basically, just smooth histogram, so to speak. And we can try to scale the x-axis, scale x logarithmically. And if the output is a normal distribution, it means that this variable has a log normal distribution. Not exactly log normal, so probably we need to think of something else. Yeah, but you can do basic plotting and analyzing continuous variables in this way. So let's move to another variable, So work class. It's a categorical variable, so we have a bunch of options there. So we can count the values, right? So we see that most people, their work is private, so they work for the private company. Some of them are self-employed, some of them work for the government. And what can we do here? So we can see that we have multiple classes of government people. For example, local gov, state gov, federal gov, and we also have multiple self-employment types, right? So we can try to merge those and reduce the number of values there. So I copy the data and I replace the values, right? So I can simply call it with a dictionary and replace, for example, self-emp not inc with just self-employed, or self-emp inc with self-employed also, right? We should also match without pay and never worked, because the counts are quite small. So yeah, let me execute this. Oops, it didn't work. So where is the problem? Yeah, so let me insert the new cell below, and yeah, let's just check the first row and the variable work class. Oh, so we can see that there is a space here. So we should probably, before we replace this, we can, for example, map it with string strip to reduce the spaces, and now it should work. Let's see. Yeah, so now it merged our categories into small number of groups, right? So we can do the similar thing with marital status. So there are a bunch of merit something values, and we can do this with a function. So we can also map this variable, the list of values, through some map function. So there is a simple function that checks whether this status starts with merit and replace this with merit, and if it's divorced or separated, just not merit, and in other cases it just returns the marital status, right? So I can execute this, and now my values are again merged. Okay, so let's start to analyze this data set in the context of our label, so the income. The income is stored as a separate data set, so I need to again read it as a CSV. And we can see that both labels and our original data has a field called ID. So this is actually the ID of the person, and we can use it to merge those data sets into one big data set with both variables and label. So this is very similar to the simple SQL join. So we just provide one data set, second data set, and the join key. So name of the field that we want to join both those data sets, right? So I can execute this, and now I have my big data set with every variable and a label. Okay, so yeah, first thing we can do is to count or to check the distribution between values of the label. So we can see that this data set is not evenly distributed. 50K, actually more than 50K. Like the imbalance ratio is 1 to 3, right? So we have 3 times more people that have income less than 50K than more than 50K. So this can be a problem for the classification task, right? Because the data set is not balanced. One interesting thing we can check is whether the sex is an important factor in predicting income. So males or females, what is the difference between the distribution of the label? So yeah, the number of males and females is quite better. It's 1 to 2 imbalance. So we can try to group this by the sex variable and compute the value count for the labels for each group separately, right? So this group by thing, it creates a separate data frame or data set for each value of this variable. So we'll have 2 data sets, females and males, and on those data sets, we check the label variable and count the values, okay? So if we execute this, we can see that actually males more often have income above 50K, right? We can also check the percentage. So actually we can conclude from this that being a female is a strong predictor for earning less than 50K. Actually, it's quite old data set, so I hope it's not true anymore. But yeah, this is what the data shows us. So I wanted to show you another cool feature that comes with iPython notebook. So we can actually create interactive widgets. So here I created a plot scatter function that takes an age variable, and I select the subset of my data where the age variable exceeds this threshold that is passed as an argument, and then I plot it as a scatter plot where x axis is age, y axis is hours per week, so how many hours per week this person works, and I also differentiate it by the sex. So yeah, so it creates a plot with this interactive widget. So I can now change the left bound of this plot. So here the value is 58, so we showed people above 58. And if I change it to, for example, 25, it will be replotted with new boundary, right? So I can interactively, test my data set with those widgets. So what we can see from that, actually, if we move it to the leftmost value, so we might conclude that females in younger age actually work a bit less hours per week than the females, for example, after 30. So we can try to differentiate this data set based on this observation. So this actually splits the data set into two separate data sets, where we, first of all, we select only females from our data set with this Boolean indexing. And then we can also select females with age bigger than 30 and vice versa, and we can compute some summary statistics based on that, right? So now we can see that females after 30, their mean hours per week is 38, and for the females before 30 it's 33, right? So it's smaller. Whether it's statistically significant or not, we need to run some hypothesis testing, right? So there is another interesting variable, capital gain. It actually shows that it doesn't make sense to treat it as a numerical variable, right? Because most of the values are 0, and there are some values that spread to up a million or 100K or something like that. So it's better to turn it into a Boolean variable. So I can do this very simply by just combining this variable to 0, and it will create a Boolean variable with true or false, whether this particular row exceeds the threshold 0 or not, right? And same for the capital loss. So if I execute this, I can see that, yeah, most of the capital gain values are actually less, 0, because it cannot be less than 0, and only some subset of those exceeds 0, and similar thing for capital loss. Okay, so that's all for the basic data analysis. Do you have any questions?
Why have you chosen 50K for the cat?
Sorry?
Why have you chosen 50K for the cat?
We didn't. So it was provided with the data set. This is the whole data set with where the label shows whether the person exceeds 50K or not.
Okay, so it's okay, fine.
Sorry?
Okay, so you don't have continuous value.
No, it's Boolean variable.
Say for instance you had that goal of looking who makes over 50K and who makes less.
Yeah.
Say for instance you want to find who makes more than 50K. Is there a way where you could just do some kind of feature extraction instead of playing through the data?
Yes. So this is the next part. Actually, machine learning and learning the classifier to predict whether a given person would exceed this threshold 50K or not.
Okay.
I would actually strongly not advise just taking the data, whatever you have, and feeding it to the first model that you have and saying like computer learn stuff for me and give me answers.
Yeah, so this is a good example, right? So if I, plotted this variable, it was a numerical variable, right? So I can, for example, scale it to for example, to have a value between 0 and 1, but it doesn't make sense because like the distribution shows that most of the values are 0 and only some of the values are exceeding, the 0 threshold. So it makes more sense to make it a Boolean variable or maybe a categorical variable with some fixed thresholds than use it as a numerical variable. So actually exploratory data analysis is a very important part of working with data. It comes before machine learning. Yeah, so let's go to the machine learning. So what do we want from the machine learning library? Well, we want a huge library of machine learning algorithms. That's obvious. We want it to be simple to use. We also need various data preprocessing, right? Because for machine learning, we need numerical data, and we need to somehow encode, for example, categorical variables into a numerical data. We want, to be able to train our algorithm, but also to validate it. So we need to split somehow our data set into test train, pair, and, for example, do cross-validation. Sometimes it's useful to search for the ideal values of the attributes, so we can do a grid search of those. And we want to persist our model and use it later in different contexts, right? So scikit-learn is a great machine learning library with very simple interface. So we'll start with preparing the data to be machine learning ready. So we need to turn every categorical variable into, for example, one-hot encoding, right? So what's that? So here's the world class variable, and it has a bunch of values, and I encode every value, every row, into this vector of zeros and just one, where the class is the class of this row, right? So I change the world class into this row of, I don't know, maybe 7 values or something like this. And I need to do exact same thing with every categorical variable, right? With numerical data, we need to scale it to, we need features to have the same scale. So there cannot be, for example, one feature with values from 0 to 10, and another feature with values from, I don't know, -1,000 to 1 million, right? Because it doesn't make sense. So we need to scale everything, for example, using the normal distribution. And yeah, so this is the piece of code that transforms the age and hours per week. Those are our numerical variables into the scaled version. And we get those one-hot encoding for the other features, including world class, education, and stuff like that, right? And then we combine it to one big training data set. So let me execute this, and yeah, so this is our final machine learning ready data set. We have all of our variables encoded as numerical features, and yeah, and labels is just, we extract this single column label, and that's it. So what's next? We split our data set into training and test data set. So this is a very simple function from scikit. We provide data and labels, and what is the proportion between training and test data set. So we choose like 30% of the data set to be a test data set, and the other 70% is just the training data set, right? So I execute this, and now in train data, train labels, and test labels, I have the corresponding values. So yeah, learning. So let's train a very simple logistic regression model, and it's very simple in scikit. So I just instantiate the logistic regression. I call one single method fit with data and labels, and actually training is done. And now I can predict values for the test data by using predict function, and then I can just combine predictions to actual labels and take a mean to have a mean accuracy, right? So very, very simple lines, and we can see that our test accuracy for logistic regression on this data set is 78%. But accuracy is not enough, especially if we have a skewed data set that has labels that are not evenly distributed. So it's useful to print precision and recall, right? And F1 score to check for the class imbalance, right? So this prints the those values for the training and the test data set. So we can see that, for example, for the more than 50K class, our training F1 score is about 90%, which is super good. But for the test data set, it's actually like 0.5. So yeah, so we are clearly overfitting there. The API is very simple, and all algorithms share the same API. So every algorithm has a fit method and predict method, and actually we can even iterate over different algorithms. So here I chose logistic regression and decision tree classifier, and we can iterate on those and test the accuracy of different algorithms, right? So here we can see that logistic regression, oh, so actually there was a mistake here, I think, because I used, yeah. Yeah, so I used a different variable. And here we can see that logistic regression is slightly better. So actually let me retrain the, oh, so it's still overfitting or not? No, it's not overfitting. So the decision tree classifier was overfitting, and we can see it from we can see it from this. Actually, let me just copy this. Yeah, and print it here. Oops. Yeah, so logistic regression is actually not overfitting. It has a bad F1 score both on training and test data set, but decision tree classifier is overfitting because it has a really good F1 score on the training data set, but bad score on the test data set. So from those two, we should actually use logistic regression.
Have you considered to prune that tree?
Sorry?
To remove the lowest leaves of the tree?
Yeah, so actually every algorithm, so for example, logistic regression actually has a bunch of attributes that you can set. So here, for example, there is a regularization method used here, L2, and you can provide, the regularization parameter and a bunch of other stuff. So the same thing is for decision tree. You can actually, let me see, what are the options there? Yeah, so we can, for example, provide max depth to prune the tree, max leaf nodes. So you can tweak it to your needs. Yeah, so the last part is once we have the trained algorithm, we can pickle it. So actually serialize it and save it as a file and use it in different contexts. Okay? So do you have any questions to this machine learning part? Yeah?
So say for instance, you don't get something that's acceptable for you. How would you go about making it better? Like, what's the process like? Say for instance it's like 50% or 60%.
Yeah, so for example, here we have a problem with class imbalance, right? So we can try to somehow make it more balanced. So for example, we can oversample or undersample our classes. So we can oversample the minority class or undersample the majority class. Actually, the state-of-the-art method is combination of those and actually even feature level, like random noise or something like that. So this is one thing. You can compute different features. So there were other variables that I didn't test. So for example, well, let me see what were the variables. Yeah. So for example, education, right? So I can check what are the values of this, and you probably can merge those two, right? So you can work more on the features and stuff like that. And you can also try to learn more powerful models, right? If for example, your model is underfitting and it's not good enough. So there are many different options, but this is not like the scope of this talk. So
like, you know, this kind of data exploration or model selection traditionally was made with, you know, MATLAB or TF, right, or sometimes R. So do you see right now that Python is somehow taking over, like it's becoming the first choice for this type of task, or do you see that because, you know, other tools are still used?
Other tools are still pretty strong. So the main competitor for what I showed you so far is R, of course, for like local small data analysis and stuff like that. But what is cool with Python, because it's a general purpose language, you can do much more with Python. So for example, now I pickle this model and I can create a web service in Django and load this model and use it for scoring, you know, request reply on a request reply basis, right? Also, sorry?
Go with Storm.
Yes, so Python has also great integration with big data. So that's like the next part of this talk. And yeah, it's just, you know, much broader language. So I think that R has good libraries too, but Python is general purpose language.
So you can basically reuse what you did during this exploratory phase in actual production.
Yes, exactly. Okay, so let's move to the big data part. Okay, so this was small data. So now let's move to the cooler part, big data. So Szymon was talking about Hadoop streaming and Apache Storm. So you can do both batch processing, big data, and stream processing big data using Python. So Hadoop streaming, this is this solution with running arbitrary script through pipes using Hadoop. But actually what's like more hot nowadays in big data world is Spark. So how many of you heard about Spark? Right, so Spark is quite different from the Hadoop. It uses this abstraction of distributed data sets that are spread across multiple machines. It has an advanced execution engine that combines the execution into directed acyclic graph, right? So similar to Storm, we have, you know, different components and they emit different like the data that is the input to other nodes. It has lazy evaluation. So when you compute like map, for example, or reduce something in Spark, it's not evaluated immediately, only when you call the special action that actually collects the data. It can keep data in memory, which is super cool for the iterative processing, and it can run on top of Yarn. So the same scheduler that Hadoop uses. And it has official Python support. So let me switch to my other notebook. So I think probably my SSH connection failed. So let me reconnect to the to my notebook. Yeah, and this is the second notebook that is actually running on top of Spark. So I have my Spark context, and to show you that I'm not kidding, this is actually listing the nodes in our cluster. So we have about 10 nodes here, and yeah, everything holds. So we have the same cool research and development environment using iPython, and now we can query our big data using Spark cluster. So very simple thing, we can parallelize the list of integers and send it across the nodes in the cluster, and this is the action. So it's actually taking the first 10 results, right? That's the opposite to the transformation, which actually like mapping this data set into squares, similarly as with this small data. It doesn't compute it immediately, it just returns an RDD. And we can evaluate this by, for example, taking the first 10 elements, like above, right? So this is Spark. So let's try to do something more. We can try the classical big data tasks, so counting words. So I'm actually loading the file from S3, and we can it's loaded as a iterator of lines, right? So we can iterate all those lines and map those lines into words by just splitting the line using spaces. And once we have those lists of words, which is flattened using flat map, we lower every word to have a common representation regardless of whether it has a capital letter or not, right? So this is our RDD with words, and now we can define a word count function that takes this kind of RDD and performs the word count. So first we map every word to a pair of word and one, and then we can reduce it by key. So every reduce task gets a word and a list of ones, actually the number of ones that this word appeared. So based on this key and the list of ones, we just sum all the ones to provide a pair of word and the count, and then we can map it and switch the order. So we have a word and count pair, and we just emit a count and word pair, like just switching the variables, right? And then we can sort by key, and if we do that, we can take the first 10 examples, and it will show us the 10 words with the biggest counts, right? So what we can see is that the top results are actually the stop words, so not really interesting words like the, of, a, and stuff like that. So what we can do, we can filter those stop words. So yeah, I'm loading another data set with stop words where every line is a stop word, like 2a and stuff like that. And we can just, using the same words RDD that we defined previously, we can filter this. We can filter words and exclude those that are stop words, basically by passing the simple lambda, right? And now we can compute the word count and take the first 10 results. Yeah, and those are the top words without stop words, actually, right? And it was done on the cluster in a distributed fashion, and actually, like you can see that it's almost, it's very similar to the data analysis part that we did previously. So very simple API, and we can do very cool stuff with it. So let me actually do some simple analysis on the adult data set that we used previously. So here's the part where we parse every row. So I'm actually splitting the row to fields and then cast every field into appropriate format. So I cast the numerical like integers to integers, like floats to floats, and every other element is just a string, so I strip it to remove spaces, and this is my row, right? So I can compute this, and this is the first row in my data set. So like very similar to the one we had previously. What is also very cool in Spark is Spark SQL. So Spark SQL is a SQL API that enables you to query your data sets that are defined as RDDs. So in order to do that, I need to do a few steps. So first step is to cast this vanilla list of fields to row from PySpark SQL. So it's just a named tuple, right? So I need to pass the name of the fields and zip it with actual fields, and then just map every record to this kind of thing. So it just maps the list to this kind of row objects. Okay, and when I have that, Spark actually can infer schema automatically. So I can parse this data set and it will infer the schema of every field. Once we have the schema, we can register this RDD as a table. So here we're registering it as an adults data set. And now we can query it using SQL, right? So here I'm computing average age from adults where marital status is never married, right? So just regular SQL, and it actually distributes this, it turns it into PySpark API, distributes this query to our cluster, and we have the result that the average age is 28. Another cool stuff is actually we can use both Spark SQL and regular Spark API at the same time. So here I'm selecting some subset of the data. So basically grouping and counting by country. So select native country and count for that country for males. And once I have that, I can use like the regular Spark API. So for example, map those records of country and count. And similarly to our word count example, we can inverse the order to count and then country, and then also sort by key and take the first three examples to see the three most popular countries.
Can you join tables?
Yes, I can join tables.
What about performance? I mean, is it very good at joining, or?
It depends. So joins are usually the bottleneck for the memory part, where you need to store, for example, for some ID, you need to join. You need to have every copy of the record from the other table. There are some tricks here that you can use. You can always repartition the data to more nodes or different nodes to make it more efficient. So there are ways to do that.
And if you have million records and you want to select one value, it will have to process all the records. Yeah? There's no indexing or.
No, there is no indexing. Yes. Yeah. So it actually computed the most popular country is United States, right? So this is PySpark. PySpark is Python in Spark is officially supported. So this is part of the official Spark distribution. And as you can see, it's very easy way of querying large data sets using very simple Python API, right? So yeah, more questions here?
You can use your own functions there? Or? Sorry? You can use your own functions.
You can.
You can?
Actually, I used function here, I think. Or only lambdas, right?
Yeah, but in SQL.
In SQL? I'm not sure, to be honest. But you can always, map, use your function in the regular, using regular Spark API, and then the resulting RDD you can register as a table for SQL querying. So I'm not sure whether you can use your functions here, but okay. And the other part is real-time big data, so stream processing. Szymon was describing the Storm, so maybe I'll skip this part. But there is a very cool framework for Storm in Python from Parsley. So here's a very simple example. You can if you install string parse, you can create a sample project, which is word count, and you can see that this is the vanilla Python implementation. So you have a spout class that emits words. So I initialize the list of words here, which is a cycle, and if Storm wants the next tuple from this spout, I just emit subsequent values from this cycle, right? And bolt is also very simple Python code. I initialize the counter, so this is a dictionary where keys are anything and values are integers. And yeah, and I can just, for every word, I increase the counter. Oops. And yeah, and emit it for further processing. So very simple API also for stream processing. And here is a small example for actually using this trained model as a Storm topology to classify adults in real time. So here's a simple spout, like similarly to the word count. We just have a list of sample adults, but of course it can come from Kafka or some database or stuff like that. And in a classifier bolt, we just need to, in initialize method, we need to load our pickled model that we trained previously, and then we can just use it in processing, right? There is one caveat here. We need to use this logic from notebook to actually turn this this row into this numerical vector. So change every categorical variable and numerical variable to appropriate format, but we can reuse the code that we actually did previously in the notebook. Yeah, and we can just use the predict method on the model that we just loaded. We don't even need to know whether it's logistic regression or decision tree classifier. Yeah, we just use it, use this method. And that's all. So do you have any questions here? Or to the whole presentation?
Have you used Luigi framework for scheduling jobs in Hadoop?
Not yet. We plan to use it very soon.
So about putting the actual prediction machine on Storm, do you know some good strategies for placing different parts of the whole process on different bolts? For example, putting the cleaning of the data, the stuff you have in this bolt, in separate one, the one that actually does prediction. Do you do something like that?
Yeah. So basically, when you design a Storm topology, you can go with, if you don't reuse your computations in different nodes or bolts, you can just do everything in one single bolt, right? But then you lose this feature of Storm to scale every single component independently. So for example, if you're actually using this machine learning model is very expensive operation, you can put it as a separate bolt that is scaled separately on different number of nodes. And if this pre-processing part is quite fast and you can, for example, fit on a single process, you can use lower parallelism level for this bolt.
So basically, you put this pre-processing separate from prediction,
Yes.
right? And then the other thing you put separately because it scales differently, or just those two elements?
Well, the splitting part is either for reusing the computation. So for example, you can have two models that are scoring in the same time, right? So you can have one pre-processing model, and the pre-processed data goes to two bolts. One, for example, decision tree classifier and two logistic regression classifier, and then can operate, in the same time, right, on the same data. And then you can join the results again, right? So, I mean, in the simplest case, you can do everything in a single bolt, but once you need to either reuse your computations in different bolts or you want to scale some parts of your bolts independently, you need to split it into multiple components.
And how you can use custom libraries in Spark and this?
On Spark. So Spark uses something called, I think it's called Cloud Pickle or something like that. So it can actually, if you have your code in your Spark master. So for example, this notebook, it can actually pickle every function that you define, and yeah, I think it even can pickle external libraries, but you need to provide them assign them to some global variables, like something like this, pandas, right? And it can pickle it and send it to your nodes without, you don't need to install your library on every node, right? But yeah, but you can, of course, sorry?
So it's pure Python libraries.
Python libraries, yes.
Pure Python.
Pure Python. Yes, so it works. Library. Sorry?
Because when you have silent library, something that is compiled from C, you install it still on the... Yes,
you have to install them. Yes, exactly. Yeah, so actually it works like Spark is JVM based. So for every node in your cluster, there is a JVM spawned and separate Python process, and they communicate via pipes. So actually, like data is stored inside the JVM, and it's serialized and deserialized while communicating with Python processes. So of course, it's a bit slower than the vanilla Spark, for example, that uses only JVM. But on the other hand, you can use the same language for everything. So that's the benefit. More questions?
Yeah. Do you find the dynamic side of Python problem with working with data? Because basically you don't have any static analysis of what your argument, you need to run it, and it's after 10 hours you will see that there is a mistake, which in Java you will see at the beginning.
Generally I think that it's not like the question is not specific to Spark. I think it's more like a dynamic versus statically compiled languages. I think that static, like checking the static types, is just the tiny part of checking whether your application works or not. So the more important part are tests, unit tests. So you can test much more things with unit tests, and you can very easily like test Spark with unit test. It has a local context that you can spawn on your local machine, that it's not distributed. And I think this is like the preferable way to test your code. So for me, it's not a problem because I write tests.
When you're running that Spark cluster, when you're running and building a Spark cluster, are there any advantages of using, the Hadoop scheduler?
The Hadoop scheduler?
So
Spark can use several schedulers. So there is Apache Yarn, Hadoop Yarn. This is one scheduler. The other is Apache Mesos, and there is like a built-in standalone scheduler. So yeah, so basically you need some sort of scheduler if you want to reuse your cluster for something else, right? So the advantage of this is you can have one single Yarn cluster, and you can run both Spark, Storm, and Hadoop on the same cluster, right? So like this is the advantage. No more questions? So thanks, guys.